Hello everyone, it's my honor to attend ASE 2022. My journal first track paper is SafeDrop, detecting memory deallocation bugs of Rust programs via static data flow analysis. I am the first author, Mohan Cui from Fudan University. From the title, we can see this work is targeted at a specific programming language, that is Rust. I think some of us are heard of this language, because it is very popular in the Stack Overflow. In this paper, we want to study the memory safety issues caused by the automated deallocation in its ownership system. Today, my talk can be divided into three parts. The first part is our motivation. Before we dive into the detail, we will first give some introduction to the Rust programming language as background. Rust is an emerging programming language and provides many attractive features like generic closure, but I think memory safety is most important. Rust adopts many novel designs to enhance memory safety. The first one is the ownership model. Ownership is quite similar to the smart pointer in the C++, and they are both deriving from the linear type theory. In the ownership model, each variable has an exclusive owner for the allocated memory. The owners are basically object types, just like string and hash map. In this model, the destructor will release the memory automatically in the proper time, or in another word, in the proper program point. This program point is calculated by the compiler, so it does not have any garbage collection, just as in Go or Java. The full calculation is in the compile time, with no runtime overhead. Since the compiler takes over the deallocation instruction, we hope this deallocation mechanism is always safe to launch. But in practice, it is not what we expected. Another feature is language separation. Rust introduces a keyword unsafe to divide itself into safe Rust and unsafe Rust. The safe Rust is memory safe, but the Rust is a system programming language. It should provide the low-level control over the implementation like C programming language. The unsafe part is necessary, but the safety should be guaranteed by users. We all know not all the programmers are carefully enough, even the Rust expert. Therefore, unsafe Rust may break the memory safety promises and affect the outer safe Rust. Now let's move our sight to the motivating example. Here we show a buggy snippet that triggers double free by automated deallocation. In the function genvec, we declare and initialize two objects. The first object is a string by using the treat from, and then we use the method as mute pointer to create a raw pointer towards the string. The key point is we use an unsafe block to call the unsafe function from raw parts and create a new vector. This function casts the first argument, that is a pointer, to generate this vector. And this string and vector, they are memory overlapping. But it is in the unsafe block. The compiler does not know that. The compiler only knows they are independent variables and need to add deallocation instruction for them respectively. As we can see, before the function is returned, the string will be freed as a temporary variable. This is safe, alright, but when we call it back to the main function, the return value becomes a dangling pointer, and this is not the worst case. When the vector is no longer usable, it will be deallocated and cause a double free. Let's see how compiler presents this code snippet. The compilation procedure is very important because the code representation is highly connected with our analysis. As a static, strongly typed programming language, Rust compiler passes the source code to a lexer and a parser to generate abstract syntax tree. Later, it's a little bit different because Rust compiler is not a traditional path-based compiler like GCC or Ceylon. It provides many queries as methods for compiler to ask for calculation. The AST will be lowering to HUR just high-level intermediate representation. It's a tree-formed IR for type check and also stripping unsafe keyword. The HAR will be lowering to MAR. MAR is a control flow graph. It consists of many basic blocks and edges connected with each other. Moreover, the ownership is implemented in MAR. The control flow graph is convenient for us to perform data flow analysis. Therefore, we implement our analyzer as a query named SafeDrop in Rust MAR. The backend is fully based on the LLVM, and it is not the key point in today's talk. Then we can talk about the insights of this motivating example. First, the issue is ownership triggered. We will see how MAR represents this code snippet. The function in MAR is a control flow graph, and the variables are renamed as numbers. In basic block 0, the desugared function creates a string, and then we create multiple references to call the function as multiple pointer. Then we highlight those variables that they are aliasing. In basic block 5, the unsafe function from raw parts takes the pointer and returns the aliasing vector. Then in the basic block 6, it clears the string before the vector returned. At last, the main function is responsible for releasing the vector and incurring a double free. So we can give the first insight. The automated deallocation is not always safe to launch in the ownership system. Second, this issue is unsafe triggered. We can see the root cause of this problem is inside the basic block 5. The unsafe function generates the reclaimed memory. Since the HAR strips off the unsafe marker, the MR does not know this function is unsafe. Even the double free was not happened in the unsafe block, but in the safe function that is main function. So the second insight is the unsafe code may intensify the memory safety errors of safe Rust. At last, this issue is unwinding triggered. As for now, we only show the part of this graph. Here we highlight the basic block 1, 2, 3, 4, 5. They are multi-branch node, and we add the unwinding edge to complete this graph. To our surprise, there is another path that will trigger double free, but it is an unwinding path. Therefore, this issue is not only happened in normal execution path, but also in the exception handling path. The third insight is very important. That is, the panicking or the stack unwinding may also trigger the memory safety errors. In this aspect, our work is highly related to the different paths, and we need to design a path-sensitive method to detect these bugs. At last, we summarize 7 typical patterns that will incur memory safety errors in ownership model. Our motivating example satisfies the pattern 2. It uses the unsafe constructor to generate the reclaimed memory and free them twice, that makes a double free. In this second part, we will introduce our method, SafeDrop, a trade-off static analysis design for Rust programming language. And now we first talk about why we chose static analysis as our methodology. Static analysis runs on source code without program execution, so it has a very high performance. Moreover, it can cover those branches which are hard to trigger, including all the unwinding entries. It is quite compatible with our study, but path explosion should be considered. The drawback of static analysis is a low scalability and accuracy. It may introduce too many false positives for users. The dynamic analysis will execute the programs with test cases and find crashes. Therefore, it will suffer from the runtime overhead. For example, fuzzing may need a couple of days to test the given programs, and it is hard to trigger all the branches, especially for unwinding. And the dynamic analysis is also limited in the library analysis. Considering the Rust is a compile time language, and ML provides a nice form of the code representation for us. And the unwinding safety is also vital for our analysis, so we decide using static analysis, especially the data flow analysis, to detect such bugs. Here we give the overview of SafeDrop. As it is implemented in the Rust compiler, it can be invoked by using Rust C or Cargo. For each function in SafeDrop, there are 3 steps in our analysis. First, it will extract all the valuable paths and analyze them independently. For each path, it will perform inter-procedure analysis to identify the reclaimed memory, then using those typical patterns to detect invalid drop methods. Finally, the potential errors with location will output to the users. Here are several challenges in our research. The first, how can we extract the valuable paths in the control flow graph? The path explosion is incurred by the branches and loops. The winding entries will also intensify the path explosion. We need to filter the unreachable paths based on some conditions because we have too many path candidates to check. Here we give 2 kinds of paths that can be shrinked. The lower path is trivial and it does not consider the path condition, and the upper one can be refined. The condition in node 3 was determined by the enum types. The variant A and the variant B, they are mutex. Therefore, enumerating all paths will produce unreachable paths. Our solution is the tangent-based graph pruning. First, we contract graph by using tangent method to remove cycles and generate spanning tree. We will meet the analysis result at the end of the path. Then we will pruning the spanning tree based on the branch conditions. We find the mutually exclusive paths that cannot be shrinking into one point, and remove the unreachable paths and resolve the confliction. Finally, we merge the redundant paths to reduce the sum of the candidates and improve the speed. Here are 2 criteria. First, the unique path is a set of basic blocks with a start node and an exit node. Second, the valuable path should not be the subset of any other valuable path. And here we give the pruning result of this graph. The lower paths can be shrinking into one point, but the others consider the branch condition which removes the unreachable paths and make corrections. This approach is fast enough to filter the path candidates. The second challenge is how can we perform alias analysis for Rust syntax? Rust has many type features as enum traits and the specific ownership syntax like movements. We can see the MLR does not have unsafe scope, so we do not need to separate unsafe Rust. Besides, the closure is same as function in the Rust MLR, and it is easy for us to analyze it. Therefore, how to fast filter those types for alias analysis, and how to establish alias relation for ownership syntax, and how to abstract the alias set is our question. We design a fine-grained type filter to fast and accurately identify non-trivial types, and we assert the enum types must associate with the variant index and check the compound types recursively, including their generics. Then we abstract the alias relation by using disjoint set union. Our work is path sensitive, so the performance of the analyzer is important. Disjoint set union can fast merge and delete the members. The following syntax dissolves the move and copy syntax, makes the alias relation general, and is also flow sensitive. Here is an example. Given A equal move B, we will delete A from the original alias set and add A to the set B. Sometimes 2 sets can be merged, therefore the algorithm is still fast. And this syntax also supports field, thus our approach is field sensitive. The third challenge is the trade-off between the accuracy and the scalability. We have talked about using disjoint set union to accelerate alias analysis, but the interprocedure analysis is still a problem. Our work is path-sensitive, field-sensitive, and flow-sensitive, but the interprocedure analysis is context-insensitive. In interprocedure analysis, we create a summary for each function. This summary is a Boolean vector that demonstrates if any parameters is the alias towards the return value, and this cache can be reusable in the alias analysis. At last, the third part is our evaluation. We will evaluate the usability and performance of SafeDrop. In the effectiveness experiment, we evaluate our tool against Rudra, ML Checker, and Miri to all existing CVEs with memory safety issues in ownership system. Rudra and ML Checker are static analyzer for Rust, but Miri is a dynamic interpreter in Rust MLR. The result shows our tool can recall all those CVEs with few false positives. Although Rudra and ML Checker support more bug patterns than SafeDrop, the performance of memory safety bugs error detection is limited. Moreover, we are the first work that studies the memory safety problems in the unwinding path. In the usability evaluation, we found more than 100 bugs inside 12 crates. Rudra and ML Checker cannot detect them because most of them are lying in the unwinding path. Finally, the performance of SafeDrop is efficient. We compare the SafeDrop with original compilation time. It shows that the overhead is close to the original compilation time, which is acceptable in setting in the compiler. And that is our today's talk. Thanks for your listening.